now we can work out calculate the acceleration of on the crate when the man is pulling it. So our forces are, we've got this one force coming out this way, 30 newtons. Okay, we've got one force coming out this way, 15 newtons due to friction. We have a weight force of the effect of the mass of the crate under the effects of gravity causes a weight force of 50 by 9.81. That's your mass times acceleration due to gravity. But at the same time, there's another force which is called the normal reaction force, which pushes back up, trying to balance out this force pushing down towards the earth. Okay, so if you consider this scenario, you can recognize we've got forces going out in different directions. This one on an angle could be broken down into one part that is a force going horizontal, and a second part that is a force going vertical, and we can break down every force on an angle into those components, that horizontal and vertical component, using right angle trigonometry. Now, this horizontal component you can see is the adjacent side of the triangle. It's actually that part itself that's the actual going to be the size of this 30 newtons that is actually trying to compete against and balance out this 15 newtons of friction. Okay, so when you're adding or subtracting forces in working out your net force, you've got to only do it with forces that are acting in the same straight line direction. That being a horizontal straight line direction or a vertical straight line direction. Does that make sense? Alright, so let's look at first what we would get for just the vertical straight line forces. Well, those forces will be, one would be the normal force going up, and we're going to just denote here, just for our reference, that going up we're going to recognize as maybe being a positive direction, and going down we're going to recognize as being in a negative direction. Right? And there is no set rule with going up as positive, down as negative. I get to choose that myself. Okay? As long as when I'm writing my net force that I'm consistent with my additions and subtractions in that same direction. Does that make sense? So if a force is going up, it's going in the positive direction, so I'm going to make sure it's going to be a positive force written in my net force sum. But going down is negative, so it's going to be a subtraction of the weight force. Now there's a third force in the vertical direction. What would that be? It's part of the diagonal. Can everyone see that? The diagonal force over here has this vertical part, its component of it in the that goes up vertically, and its size, because it's going upwards is positive, so I'm going to add on to that the size of this side of the right angle triangle, and you recognize that's the opposite side of the right angle triangle. What trigonometric ratio would I use to work out the opposite side of that triangle? Sine ratio. Okay, so what would the expression be? 30 times sine of 45. Very good. The opposite side is calculated as the hypotenuse multiplied by sine of the angle. Does that make sense? Everybody understand? Okay, so that's our net force, all our net forces, all our forces to form the net force in the vertical direction. And Newton said that the sum of all the forces must be equivalent to what? Mass multiplied by the acceleration of the object. Okay, now this, when we talk about acceleration, we're only considering in the perspective of the vertical direction. So in this scenario, think about it logically. Is the crate going to move or accelerate vertically? No. Yeah? No, not really. Only perhaps if the object, the man or whatever object was exerting a force on the crate on an angle, if that was done with a certain size force that was large enough, what could he actually do to the crate? He could lift it off the ground. Okay? So the crate could, in fact, accelerate vertically a little bit if the pulling force, if the tension force is large enough. Okay? But at the moment, it's just sliding across the ground, and so the acceleration is going to be 0 because there's no vertical motion. Yes, Ashley.
Oh, no.
Say again. When the velocity is constant, the acceleration is 0. That's correct. Yes. Well, if he was already in motion and he already had some initial velocity and he was moving, then the same thing applies. The only thing that could change is the type of friction, because and we will examine the difference between what's called static friction and kinetic friction. Okay? And then the other thing that will apply, that what force relates to, is acceleration. And acceleration is about how speed changes. Okay? This is only working out how much the speed of an object is going to change by. And if the object is stationary, then it's all about commencement of moving from a stationary position into a, picking up speed or state and starting to move. Yeah, but if the object's already moving, say it's already just traveling, is dragging along nicely at 1 meter per second, and he can keep doing that as long as all the force is balanced. But if he pulls a little harder, he can accelerate the crate and make it speed up a little bit more.
An object is stationary.
Yep. Yep. Okay, so that tap changes its velocity, but the tap is just one single push. You tap once and then you take your hand off it. Yeah? So you're no longer applying a force when you're not haven't tapped it anymore. That's correct. You apply force since you have to keep on applying it, like pulling on a rope constantly. A tap is just one single applied force, okay? But you would have to continue to push it and at that same force. All right, so what could we do with this vertical component? Because this is not answering our question about acceleration, but what we could see is there's, out of the forces we have here, the one that is unknown, then if we worked out sine of 45 approximately on the calculator, you would see that's about 0.71, and that is equal to 0. Okay, what could be the goal of this equation? What could we be working out the size of? what is it called? N? What is N? Son? Normal force, thank you. So it's possible to calculate the size of the normal force. Okay? We get 49 minus 0.7 lots of 30, which is about 21, 22. And what's that? That is 28 newtons approximately. Okay, so the normal force actually is going to be an important part looking at our next piece of learning on the incline plane. But let's continue and finish our task of working out the acceleration that's going to experience. So you have to recognize that if I'm interested in the acceleration, I got to think about it logically, and I recognize, well, if it's just sliding along the ground, the acceleration is happening horizontally or parallel to the motion. Okay, so I got to consider the forces, all the forces acting in that same horizontal or parallel direction. Does that make sense? So the horizontal forces our net force of all the horizontal forces, well, we've got two directions. We've got to the right and then to the left. So we need to also consider which direction horizontally we would consider as a positive direction, which way we would consider as a negative direction. And generally we could say, well, if we're going right, we could say we're moving positive direction, where if the force is going to the left, it's in the negative direction. Does that make sense? So if I'm applying that to this diagram, my net force, I've got 15 newtons in this direction. How should I be writing that in my net force expression? Negative 15. Very good. It's got to put a minus sign in front of that 15, because if I decide that to the right is positive, to the left is negative, any force acting in that net left direction, I must express with a minus sign. Okay, and then I've got this force here, which is part of the tension pulling force, which is happening in the positive direction. So I put an addition in my net force expression. Now, what's going to be the size of that force? Who could tell me how I would calculate that? 30 multiplied by the cosine of 45 degrees. Very good. 30 multiplied by the cosine of 45 degrees. Okay. And then that is equivalent to the mass multiplied by the acceleration of the object in the horizontal direction. And it's this acceleration that's the key to the question, because the object is accelerating or moving horizontally. Now, who could tell me what quantity you got for your net force? What did you calculate here? Mitchell. 6 newtons, negative 50, plus that, it's approximately 6, a little bit more, 6.2. Very good. Is equal to the mass of the object, and the mass of the object is 50 kilograms times acceleration. So therefore, what would we do with that to calculate the acceleration? What would be the next part? Divide by 50. Very good. So I go 6.2, the value of my net force, divide by the mass of 50 kilograms, and I get a 0.12 meters per second squared, approximately. Okay. Any questions, please? So the goal to these problems is whenever you have a force on an angle, you've got to recognize, hey, I need to break that down into a horizontal part, which is the adjacent side of the triangle, and then a vertical part, which is the opposite side of the triangle. Okay? And then when I write my net force equation, I got to do two versions. I got to consider the vertical part and then the horizontal part, especially if the question is after a certain thing. For instance, if the question asked, calculate the size of the normal reaction force, which part of the net force would be the most important to consider? The vertical component, very good. Question asked, calculate the acceleration of the crate, which part would be the most important to consider? Miguel? The horizontal part of the net force, very good. So you've got to think about the goal of the question and which direction is that quantity lying, either vertical direction or horizontal direction. Any questions, please? Now, marvelous. So what we're examining more now is understand the motion of the inclined plane. The last lesson we started to look at all the forces. All the forces acting on the inclined plane. There they are, that's what we established last lesson. So from that, on a free body diagram, we could see that the weight force is the one that is at a different angle to all the other forces. The normal reaction force here and this pushing force and perhaps this friction force, what angle are they all at to each other? 90 degrees. Can everyone see that? They're all perpendicular to each other. That's 90 degrees there. That's 90 degrees there. 1, 2, 3. These two are parallel. This normal reaction force is perpendicular. Okay? But the weight force is at an angle. And if the angle on the incline is here, geometrically what happens is that translates to the weight force being at an angle, an equivalent size angle here, and then we've got the components, its components. On this side here, on the vertical, this adjacent side of the triangle, and then the opposite side of the triangle here. Okay, now what's very important is thinking about the overall direction of those forces, those blue dashed line forces. Because look at the weight force. The weight force is going, starting here and going straight down and ending here. So if you use the blue arrows as an alternate path to get from your starting position to your ending position as shown by the force arrow, then you would have to travel along this way, follow that direction, this downwards direction, and then you're going to have from here travel across. Does that make sense? So if you follow the triangle as an alternate path to get around from one point to the other, that tells you the directions of those component forces, the horizontal and vertical component forces. Does that make sense? All right. So from this, let's see if we can break down and write an expression for the net force, for the horizontal part and then the vertical part. Actually, we're not going to call it vertical because they're not really vertical from our perspective, are they? Okay, so what's important here, because the whole thing's on an angle, it's not really vertical to our page or horizontal to our page. Does that make sense? So we're going to use different words to describe those parts, not vertical and horizontal, but we're going to call them parallel and identify the parallel forces and perpendicular. Now, the question is, what are these forces parallel and perpendicular to? Who can tell me? Ma'am? To the incline. Yes, very good. Parallel and perpendicular to the incline. But more specifically, what aspect of the object's motion is it parallel and perpendicular to? Not just the center of mass. The direction of motion. That is the acceleration. Can everyone see that? So you've got to consider the crate's direction of motion. So the crate's direction of motion is its acceleration. And if it's been pushed up the plane, you know that the crate is just going to move in that direction. Hey, so then, what are all the forces that are parallel to the direction of motion? And what are the forces that are perpendicular to the direction of motion? Okay? That's the goal. So, let's see if we can identify them and figure out their right direction, positive or minus sign. Now, in thinking about direction, we got to set ourselves a little Cartesian plane or a little indicator to tell us which way is positive, which way is negative. So, would I do it like this? To indicate my direction? No. What should I do to my little coordinate system or directional arrows to indicate direction? What should I do with it to make it appropriate? I've got to rotate it a little bit, don't I? I've got to rotate it so that one side is in the same direction as it's actually moving. Acceleration. So for this problem, everything's on an angle. So from here, I've got one direction which is going up the plane or parallel to the plane, and if it's going up, I'm going to say that is the positive direction for the parallel forces. So that means going down the plane, that is still parallel, that must be the negative direction for the forces. Okay? And then same with the perpendicular forces. Going up out of the plane, up this way, that will be the positive direction. Going inwards to the plane, going down this way, that will be negative direction. So you've got to position, in this case, for your incline plane, you've got to position your little coordinate arrows on an angle as well with the incline. Any questions regarding that? Yes. The weight force, in this case, this one going down is at a wrong direction to this orientation. So you've got to consider the components of the weight force. Yep. Okay, parallel forces. Who can name me one from referencing the forces in our free body diagram? Which one is parallel to the plane? Parallel, which is horizontal to the plane. An applied force, very good. F. That's the first guy. That's going up. And because it's going up, it's in the positive direction. So I'm just going to write it as a positive F force. Okay? Now, what's another force in the parallel direction? Friction. Friction is there it is, it's going down. Negative direction, so I have to write it as minus the force due to friction. Okay? Good. Now, is there another force that is parallel? What do you notice, Ashley? The part of the weight force. Very good. So the weight force here, it actually has a parallel part or component, which is this one here. All right. Now, let's see if we can figure out the size of this part. For instance, what side of the triangle is this bit here? It's the opposite side of the triangle. It's opposite to the angle. Yeah? So what trig ratio would we use to work out the opposite side of the triangle? Sine, the sine of the angle ratio. Okay, so this part here will be the hypotenuse. How big is the hypotenuse? W. Hypotenuse multiplied by the sine of the angle of incline theta. And what do we know about the weight force W? What's that equivalent to? Miguel, do you remember? Mass times gravity, very good. Mass multiplied by acceleration due to gravity by sine of the angle. Perfect. So that is also part of the parallel forces. What direction is it? How am I going to include it in my net force equation? Should I add it or should I subtract it? Subtract. Very good, because it's traveling downwards back this way, which is coming this way in the negative direction. So I have to subtract the weight multiplied by sine of that angle of incline. There you have it. That will be your net forces. All your net forces in that parallel direction. Now, the sum of all forces is equivalent to what? Mass times acceleration. This is Newton's law. Okay, so you can't forget what I've written down is actually equivalent to the mass of the crate multiplied by the overall acceleration in that direction. Now, because it's the parallel direction, which is parallel to the direction of motion, it actually has acceleration in that parallel direction. So it's equal to mass multiplied by acceleration. Okay? So from that we can get a little rule or equation for the actual acceleration of the crate on an inclined plane if it's being pushed in this scenario by dividing by the mass. Now when I divide by the mass, I've got 1, 2, 3 parts I'm going to divide the mass into. Yeah? So the whole lot is being divided by mass. So I need a pushing force minus a force due to friction subtract, then I need to have the mass multiplied by the acceleration due to gravity times sine of the angle. And once I work that out, the whole lot is divided by the mass of the crate, and that gives my overall acceleration that the crate will experience up the plane. Kilograms, absolutely. So this here is measured in kilograms. All right, and then what will be the units of the acceleration? What should that be measured in? Meters per second squared. Fantastic. Okay. Let's see if we can do the same for all the perpendicular forces. What do we have? Well, think about this perpendicular direction now. You can count perhaps two. We've got one coming up this way and the other one coming down this way. What do we know about this force coming down? What would that be equivalent to? First think about the side of the triangle. What side is that? Adjacent side of the triangle. So what trig ratio do we use to calculate the adjacent side of the triangle? The cosine. Very good. So this will be the hypotenuse, which is the weight force, mass times gravity, multiplied by the cosine of that angle of incline. So what will be the expression for our perpendicular forces? Normal. Good. And then minus. So the normal in one direction, which is in the positive direction, and then I got to add up the other force that's perpendicular, so subtract, because it's going down. mg cosine of the angle. Perfect. Now, at this point, the sum of all forces is equivalent to mass times acceleration. Okay? But is there actual acceleration going to be observed perpendicular to the plane, to the direction of motion? No. Because we know by just common sense, when we push a crate up a plane like this, it's not going to bounce off and head off in this direction. Okay, so that will go to a 0, because there's logically, when we think about it, there is 0 acceleration in this perpendicular direction to the plane. And you've got to use a bit of common sense. Okay, so then what does this tell us? That the normal force is balanced out by the cosine trig ratio of the weight force. And that's a cool little equation, because it actually gives us a way to calculate or measure the size of this normal reaction force, being just the mass times gravity multiplied by the cosine of the angle. So Newton's law in this scenario gives us ways of determining two facts about this scenario. We can work out the size of the normal reaction force. We can work out the size of the acceleration experienced by the crate itself up the plane. Sorry? mg is the size of the weight force, which is always vertically downward. But to be able to for the weight force to contribute towards balancing the other forces, a part of the weight force goes towards balancing the normal reaction force, and another part of the weight force goes towards help to balance out the other two forces, the push force and the friction force. So the size of those parts of the weight force are given by the trig ratios of the weight force amount, mg. Does that make sense? So this weight force is very popular. He's got two parts. He's got all those forces to try and balance out. He's got to share himself to try and balance out those other forces. Okay? And the way he does that is through geometry, the angle, depending on the angle of incline. Alright, so let's see if we can apply that quickly to a specific example, and then I'm going to, the next part of our session, we're going to focus on a little practical task where I'm going to get you to perform a motion experiment, either as an inclined plane experiment or a falling object experiment. And I want you to capture the footage on your device, on your phone. Okay? So let's see if we can break this down. We're going to look at more carefully here, specifically a more simple scenario of what we just examined. Now, this one's going to be a lot easier because this time I want you to think about what information in the question helps us to identify what forces are actually there and which ones are no longer there. And always draw the forces on your diagram first. Okay? And identify, well, what's going to be the actual direction of motion that's going to occur. Alright, 5 kilogram mass slides down. Okay, position at the top of an inclined plane at an angle of 30 degrees. Assume no friction. Label the normal reaction force on the diagram and calculate its size. Label the normal reaction force on the diagram and calculate its size. So, in this scenario, the mass of 5 kilograms is just sitting on the top of a plane. If there's no friction, what do you expect to happen? It's going to slide down. Yeah, it's just going to slide down. Yeah, so we already have an understanding about its direction of motion. Does that make sense? Just by thinking about it logically. So it's going to slide down this way, and that means its acceleration is in this downwards direction. So if it's the actual direction of motion is going downwards this way, how would we identify how can we describe the direction of the normal reaction force? Perpendicular. Perpendicular to what? To the incline or the direction of motion, absolutely. So it's the normal reaction force has to do with the surface here pushing back up on the block of mass. And that is out this way at 90 degrees. There's our normal reaction force. Now, what's the angle between the normal reaction force and the acceleration? 90 degrees, absolutely. And that's good because this can help us identify a little orientation of forces, and we can identify which way is the positive direction in the parallel or perpendicular path. So if we're traveling parallel going down, what direction should we decide that to be? Positive direction, very good. If we're going perpendicular coming up out of it this way, what direction should we decide that to be? Also positive direction. Alright? That means going that way would be negative direction, or going down that way would be negative direction. Okay, let's calculate the size of the normal reaction force. Now, you always do that from Newton's second law. That says the sum of all the forces must be the same as mass multiplied by acceleration. You always start with that. Every exam. Anything involving forces, you always start from Newton's second law. Okay, now, can we conclude anything about maybe one part of that Newton's second law? Like for instance, the right-hand side. Overall, what do you think this should be equivalent to? We're trying to consider the normal reaction force. This is in the vertical direction, yeah? This is in the vertical direction. So, if you're just breaking it down and considering only the vertical direction forces, what should that sum of forces be equivalent to? 0, absolutely. 0. Does everybody understand that? Because that means its acceleration, A, it has 0 acceleration in this perpendicular out of the plane direction, because it doesn't bounce up, does it? It just slides downwards, parallel to the plane. So overall, it's going to equal to 0. So we know that it's going to equal 0, but what forces will equal 0? What sum of forces will equal 0? That's what we're going to work out now. Well, let's see if we can identify all the other forces on it. We've got the normal reaction force, because it's in contact with the surface, is another force. Weight force, which way does that go? Straight down. Mass times gravity. Okay, the weight force is equal to mass times gravity. Okay. Now, this one is on an angle, isn't it? So, we got to break it down into its parts. We've got one part that is perpendicular, and we've got another part that is parallel. And for 30 degrees here, on the incline, where would be the corresponding 30 degrees in the triangle parts of this weight force? At the bottom or at the top? It is always at the top. Why? Well, we can determine that by examining the geometry more carefully, okay? Instead of making that its own little mass problem, and I'll show you that to you over on that board very shortly actually, but for now, if we rotate this right angle triangle here, and it's just about thinking about this big one. We rotate this one in such a way such that the point there is positioned in a way to match this size, this triangle we've drawn, where we'll notice that the 30 degrees will have to go there. If we get that corner to go there, it will pop up such that that angle there will appear there, just by rotating that right angle triangle. Okay, flipping it. You've got to rotate it, you've got to flip it. And you'll get it in that exact same spot there. No. Try it. Actually think about it more carefully. Now, let's get all the forces that add up together. What am I going to write down for my sum of forces? It's one force. Normal reaction force. Good. Positive or negative in front of it? Must be positive. Very good. And then what's the next force that's in this perpendicular direction? The weight force part. Is it the whole weight force, mg? No. It's a part of it. Which part? The adjacent part. That part there is the adjacent part. Can everyone see that? Yeah. So the adjacent part as a size, the length is determined by the hypotenuse. Hypotenuse, which is the weight, multiplied by what? Cosine of the angle. Now, what do I do with this part of the weight force? Do I add or do I subtract? Absolutely. Subtract the mass times gravity of cosine of 30 degrees. Okay? Now, I use this now to determine the size of my normal reaction force. So what would N be? How would I determine what the normal reaction force would be? What would I do to my equation that I've written so far? I'll just add it, wouldn't I? I would add this term to the right hand side, and I'll show that the normal reaction force must be equal to the mass times gravity times cos of 30 degrees. Now the mass is 5 kilograms, acceleration due to gravity is 9.81, and cos of 30 degrees is 0.866. We'll say approximately 0.87. So in other words, about 87% of the weight force, the actual weight force, 87% of the actual weight force goes towards balancing out this normal reaction force, which is pushing it off the plane. Okay? We know it doesn't actually jump off the plane because those two forces are balanced out. So what amount did we calculate? 42.5 newtons. Okay? Fantastic. Label the direction of acceleration and calculate its size. Well, there's the acceleration, and we're going to work out its size. So to work out its size, what do I have to start with? What should I start with, Sinai? When I'm trying to calculate acceleration now, okay, what rule do I use to be able to do that? Perfect. Net force is equal to mass times acceleration. Perfect. Start with Newton's second law. This tells you identify all the forces acting in this parallel direction, same as the acceleration. Then I multiply by the mass and times the acceleration. So now, because this part, assume there is no friction. There's no friction force now. Is there any forces acting horizontally? Which part? This bit. It's just this one part of the weight force. Everyone see that? That's the only horizontal or parallel force. And it's going downwards in the same direction as the acceleration, and we said going down is positive. So, what is the size of this part of the weight force? Mass times acceleration due to gravity, that's the hypotenuse, the weight force, times what? The sine of the angle, like so. And that is equivalent to mass multiplied by the actual acceleration experienced. Okay, so then what would I do from that equation to determine the acceleration? Divide by the mass. And notice over here I've got a factor of mass on this side of the equation as well. So if I divide by mass on both sides, it's dividing itself here on the right, cancelling itself out, isn't it? So acceleration in this scenario is just the gravity, but sine of the angle. That there is a little useful rule for sliding down an inclined plane where there is no friction. So the acceleration is 9.81 multiplied by sine of 30 degrees. If you did that on the calculator, you'll get a 4.9 meters per second squared. Everybody understand? So now we end up with the final question. So this could be an extension. If you know now the actual acceleration that the object is experiencing, and it's a constant acceleration because this only depends on the angle and it depends on the acceleration due to gravity. Both of those things won't be changing. They're constant. So we have a constant acceleration down the plane. All right. So now, because we know it's moving at a constant acceleration, we can determine other things like distance and time of travel and velocities achieved. If the inclined plane is 50 centimeters long, how long does it take to reach the bottom? Okay, so if it's traveling 50 centimeters long, it's undergone what's called a displacement of 50 centimeters. Although 7 centimeters isn't a very good measure of distance that matches with acceleration and with force. What should I convert that to? Meters. 0.5 meters. Okay, we've got an acceleration of 4.9. We've got a displacement. Now, let's say that let's make an assumption here. The mass was just propped at the top and then let go, and then it starts to slide down. What can we say about what's happening to the mass initially? It starts from? Initial velocity is 0. Well done, Mitchell. Initial velocity is 0. So initially, u, which we denote for the initial velocity, when it is just released from a starting position, it's got an initial velocity of 0 meters per second. And how long does it take? So what's the goal of the question? Calculate time. Okay, so I have an acceleration A, I've got a displacement X, I've got an initial velocity of 0, and our job is to determine the time. So what rule, kinematic rule, allows us to calculate time? There's time in it, there's displacement, there's initial velocity, and there's acceleration. Who can identify the key rule? Almost. What is it, John Ray? Perfect, that's the one. Read it out to me. Perfect. Instead of d for distance, we're going to say x for displacement. X equals ut plus half a t squared. Fantastic. So let's substitute the quantities we know. X is 0.5. U is 0. So we've got a 0 multiplied by time plus a half of the acceleration. Acceleration is 4.9 times t squared. Time is the goal. Okay? So we've got to transpose and solve for time. Time would then be the square root of, so that's a 0, so that goes away. So we've got a half here on this side. To solve for time, we've got to multiply by 2. So we get 2 times 0.5. And then we've got the acceleration 4.9, that's multiplying the t. So to solve for t, we've got to divide by 4.9. There we go. And because it's t squared, to solve for t, we've got to do the square root. And that's how long it will take. How many seconds? What did we achieve? Buddha, what'd you get? 0.45. 0.45 seconds it's going to take to slide 50 centimeters down the plane in this scenario where there's no friction. Things are very fast when there's no friction. Okay. Very good. Does everybody understand? Everyone see how it connects from starting with knowing forces acting on a mass, use Newton's second law to determine the acceleration, and once you know the acceleration you can examine its motion and look at displacement, look at velocities using our set of formula we have. Very, very good.